Good morning, one and all. So today is 11th of July. This is an extra session which is being conducted and for module 5. So last 2 days, that is on 9th and 10th of July, 9th July, we started this module, that is state variable analysis. So in that, we had seen the basics of state variable analysis, and we had seen RLC series circuit, how to find the state variable modeling for that. So for different three cases, that is three different output cases, we have found out what are the different state variable models for RLC series circuit. That is when output is equal to IT, output is VCT, and output is VLT. For all these three cases, we have found out what is the state variable model for series RLC circuit. So that is the only numerical we have done so far. Then yesterday what we had done was I gave you actually a state variable model, that is x dot t is equal to ax plus bu kind of thing, and y is equal to cx plus d. There I asked you to convert that state variable model into transfer function. That means how to find a Laplace domain transfer function from ABCD matrix when it is given. That was one type of numerical we had seen yesterday. After that, what we had seen was I gave you a system equation in differential equation form, that is y double dot t plus something of y dot t plus something of yt is equal to some coefficient of x dot t plus xt. So where yt is the output and xt is the input. And I asked you to find out what is the system transfer function is in Laplace domain from that system state equation. After finding out the transfer function, you had converted that transfer function in Laplace domain into the companion form. And from that companion form, you had found out what is the ABCD matrix. So initially given us a differential equation of second order numerical, what we had done. From there, we had found out the transfer function. Denominator we found is it was having a second order polynomial in S square. Numerator was first order polynomial, 4s plus 1 or something it was in yesterday's numerical. But from that transfer function, we could find out what is the companion form. And it is possible to find out the ABCD matrix directly from the transfer function. But if you are finding the companion form, which is also called as realization, that means system realization from given system equation. So realization helps us to find out what is the ABCD matrix. So ABCD matrix finding is nothing but called as the state variable representation of the situation. So system equation, differential equation. From there, find transfer function in Laplace domain. From Laplace domain transfer function, find what is companion form, which is a realization or a schematic representation of the system given by the transfer function or given by the differential equation. From that companion form, we could find what is ABCD matrix. And when ABCD matrix is found, from ABCD matrix, we can again go back to the transfer function. So we had shown you that initially whatever differential equation is given, and from there we found transfer function. And after transfer function, we found companion, then again ABCD matrix. And from this ABCD matrix, we had used that formula C into Si minus A inverse into B plus D. And we found transfer function. So that transfer function and initially transfer function was same. So this was the numericals we had seen yesterday. Today, again, we will be seeing some of the numerical in the same line. So we are in this extra session, which is being conducted on Saturday. We are not going to see anything new. Okay, so only we are going to see different types of numerical, and the level of the numerical will be a little higher. So I have some 3-4 numericals here planned for you today. So yesterday we had seen a second order system. That means denominator equation was a square. But today I'm not giving you a differential equation. Instead, I'm giving you directly a transfer function, which is little more complicated. So it's a denominator you can find, it's a third order polynomial. That means if you are finding its differential equation, which you can find very easily by cross multiplying. So ys by us in this case is the input, not xs, and u is not unit step. Okay, so us is another representation of the input. So either xs can be given or us can be given. You should not confuse it. So whatever is the symbol given, you have to go ahead with that. If I ask you how can you find a system equation, that is differential equation, from here, what you have to do is you have to do the cross multiplication, and then you have to do inverse Laplace transform. So what will be the differential equation for this system? It will be d3y dt3 plus 2 of d2y dt2 plus 3 of dy dt plus yt. I will repeat. If you are doing the cross multiplication, so you will get ys multiplied by denominator is equal to us, which is the input, multiplied by numerator. After that, you have to do the multiplication ys with the all the s cube and 2s square, 3s plus 1, and us you have to multiply with s square and 3s plus 2, and then you have to do the inverse Laplace transform, and you will be getting what is called as the differential equation of the system, or which is called a state equation. What will be the state equation or system equation? It will be d3 yt dt3 uh, plus 2 d2 yt dt2 plus 3 dyt dt plus yt. That will be in the left side. Right side it will be d2 xt dt2 plus 3 dxt dt plus 2 xt. Okay, or instead of x you have to write ut. So what will be in the right side? That is d2 ut dt2 plus 3 dut dt plus 2 ut. So ut is the input and yt is the output. So all those things are understood by us very easily. What is the next question? So question is given as in the top. You can see that from the given system transfer function, that is hs, find out the companion form representation, which you can find here below shown, or which is also called as realization or circuit schematic or system schematic of the complete system. Second, from the companion form, find out the ABCD matrices. So companion form actually helps you to formulate ABCD matrices very easily. There are processes: canonical form 1, canonical form 2. From this transfer function, directly you can write down ABCD matrices. So I will teach you that also. But first, let us find out the ABCD matrix through companion form, which is a more easier way to understand. So now see, how can we find the companion form? So I told you that central line. So central line, there will be summer, there will be integrator, there will be summer, there will be integrator, summer and integrator. And output will be yt, and yt is equal to q1t. This is a standard process we have to follow. And this is q1t, and before integrator it will be q1 dot t. So if you are integrating q1 dot t, you are going to get q1t. Okay, so reverse process is like a differentiation. So a reverse of from right to left of integrator, if you are going, means actually you are going the reverse process of integration. So that is differentiation. Better you see from left to right. So q1 dot t is there, you are integrating, you are getting q1t. q2 dot t is there, this is the second integrator, you are integrating, you are getting q2t. q3 dot t is there, you are integrating, you are getting q3t. So if I give you denominator s to 4, that means left side there is another summer and integrator that you have to add. So yesterday we had done a square plus something of s plus 1, that was the denominator. That's why we had used only 2 summer and 2 integrator. But today numerical is little more of higher level, so there are order is 3, hence we are using 3 summer and 3 integrator. So whenever you are preparing for this module, start from the first topic and see everything and go ahead. Just don't skip something in between. In that case you are going to miss the link. Okay, so now it is there. So top you are finding there are 3 amplifiers which are there, and this is the first amplifier with ut. So ut is the input, so numerator is s square plus 3s plus 2. So all the top amplifier coefficients will be same as this coefficients of s square and 3s and 2. Okay, and s cube term is missing in this case, you find. So the first amplifier will be having a gain of 2, second amplifier will is related to s, so this will be having a gain of 3, and this rightmost amplifier will be having a gain of 1. Okay, so there is no s cube term. That's why it is s square plus 3s plus 2. S cube is there at the denominator, but numerator it is starting from s square. So coefficient of s square, which is 1, comes to the rightmost amplifier. Coefficient of 3s, that is 3, comes to the middle amplifier. Coefficient of the constant, that is 2, it comes to the leftmost amplifier. Now suppose I'm giving you a case. I'm still supposed to explain the below part, denominator part. It is also very easy, so let me explain it first. So s cube plus 2s square plus 3s plus 1. So s cube, first thing we have to check is the coefficient of S cube is 1. Okay, had I given you a more complex transfer function with S cube with having a coefficient of suppose 5, in that case first step will be divide numerator and denominator all coefficients by 5 and make the S cube coefficient as 1, and then only you could proceed. I explained this thing to you yesterday also. So in this case S cube is already 1, so no need to worry, it is in the form, and q1t is equal to yt. So this 1, this constant, okay, it appears in the leftmost corner, and this yt is coming or q1t is coming, and it is a feedback kind of thing, and this amplifier will be having a coefficient of 1. Then 3s, okay, so this middle rung, this rung is for s, left rung is for constant, right rung is for square. Okay, so whatever is the coefficient constant that will come in the left rung, okay, that is 1, and here is a negative sign. The signs are very important. Top every sign is positive, bottom all the signs are going to be negative. So below it is coming to be minus, and here it is actually 1. Then this is 3s, so this yt is coming and it is actually going with a coefficient of 3, and after that here it is coming and with a coefficient of 2, and all these things are negative. So s cube plus 2s square plus 3s plus 1, it is given like this. So this is 2, this is 3, and this is 1, where this is 2, 3 and 1. So whatever is the left to right, and the below it comes to right to left. This is the thing you have to remember. Top also s square plus 3s plus 2, but while writing we write 2 and 3s and s square. Okay, so whatever is given in the equation from left to right coefficients, while putting it in the schematic form or companion form, the coefficients appear in the reverse direction. So this is how you have to remember. So now the companion form is drawn, and from here very easily we can write down three state variable equation. So what are the state variables now? q1 dot t, q2 dot t, and q3 dot t. And this is the standard procedure. So as soon as you draw this, at the extreme side you have to write q1t, and that is a yt. So output equation yt this we know. Okay, and this is q1 dot t, then this is q2t, this is q2 dot t, this is q3t, this is q3 dot t. If there was another thing, it would have been q4t and q4 dot t accordingly. Now let us find out what is q3 dot t. So first find out what is q3 dot t. So q3 dot t we are finding this is equal to ut into 2, so 2 into ut, and yt is coming with a negative sign. So q3 dot t is equal to minus of q1t, because yt is equal to q1t. That is output equation. So you can see that this q1t is coming with a negative feedback to the input. So q3 dot t is equal to minus q1t plus 2ut. So minus q1t is coming from here, then it is getting multiplied with 1, then negative feedback. So this is minus q1t plus ut into 2, so plus 2ut. Generally, in state variable representation, we represent the differentiation of all state variables is equal to first state variable with some coefficient, second state variable with some coefficient, third state variable with some coefficient, plus input with some coefficient. So in this case, where there are three state variables, each equation, so there will be three q dot equation. So each equation will be having coefficient and first state variable, coefficient second state variable, coefficient third state variable, and coefficient of input. So q3 dot t we have found out as minus q1t into uh, 1, that is minus 1 into q1t plus 2 into ut. Samely, you can find out what is q2 dot t. So what is q2 dot t? You can find there are three terms coming. So first term is q3t. I missed the arrow in the center, so please draw the arrow in the center. So here everywhere there will be an arrow. Okay, so an arrow should be from left to right. So q3t will come. So whenever you are writing q2 dot t equation, first term will be q3t. Okay. Next term will be minus 3 q1t. So this q1t is coming here, getting multiplied with 3 minus. So minus 3 of q1t. Okay, so this is q1t minus 3. So minus 3 q1t is coming from the bottom. From the left it is coming q3t, and from the top it is coming 3ut. So q2 dot t equation is minus 3 q1t, which is coming from bottom. From the left to right it is coming q3t, and from the top it is coming 3ut. So these are the three terms we are finding in q2 dot t. What about q1 dot t? Q1 dot t is nothing but there will also be three terms. One will be q2t, one will be minus 2 q1t, another will be 1 into ut. So q1 dot t, there will be three terms. One is q2t, which is coming from left to right. Okay, this is the central line. One is coming from the bottom, that is minus 2 of q1t. One is coming from the top, that is 1 into ut. So these are the three state variable equations. Okay, so q1 dot t, q2 dot t, and q3 dot t. And now what you are supposed to do is you are supposed to put all these three equations into a matrix form. But before that, I will tell you the output equation. It is very easy. Yt is equal to q1t. That means if you multiply the C matrix and the state variable matrix. So state variable matrix in this case is having dimension of 3 cross 1 because there are three state variables. So if you just multiply the C matrix with state variable matrix, we are going to get q1t plus 0 into q2t plus 0 into q3t. That means yt will be equal to q1t. It is as simple as that because we have defined initially or nothing is mentioned. So we took the liberty of defining yt as q1t. Now represent these three equations, that is q1 dot, q2 dot, and q3 dot. So left side of the state variable representation is called as q dot. So q dot is nothing but q1 dot, q2 dot, q3 dot in a column form. So left side you can also write qt is equal to, and this q1t, q2t, q3t, these three things also you can write as only qt, but that qt you have to show in a matrix. Okay, so that is when you grow up, when you get matured, automatically you will understand. And this dimension of this A matrix, so as there are three state variables, dimension of A matrix will be 3 cross 3. We have found it there. So if you're writing q dot t, and if you're writing qt here, instead of writing this 3 cross 1, if you're writing q dot t and if you're writing qt, just look at the A matrix first, and you are finding A matrix is 3 cross 3. That means you will automatically understand that this Q matrix will be 3 cross 1, this Q dot matrix will be 3 cross 1. This is automatically understood. And whatever is the dimension of Q matrix at the top, the same will be the dimension of Q matrix in YT. But in this case, you are finding there is no D matrix. That means input is not directly connected to the output. That also we can find out. Okay, and what is the A matrix and B matrix? Let us find out. So from in Q1 dot T, we are finding there is minus 2 Q1T. So this is minus 2. There is 1 Q2T. So that's why this is 1. And there is no Q3T. That's why the coefficient of Q3 is becoming 0. So how to find Q1 dot T? This is minus 2 into Q1T plus 1 into Q2T plus 0 into Q3T. That means this equation plus 1 into Q2T. So if you want to get q1 dot t, you have to just multiply this top row with this column plus top row with this column, and then you are going to get the top equation of dot t. How to get q2 dot t? This is the second row and the column you have to multiply. So minus 3 q1t you are finding here. There is no q2t in q2 dot equation. So q2 dot equation, there is no q2t. Okay, so there is no hard and fast rule that in every differential, that is q2 dot, q2 must be there. It is not that. Okay, it might not happen or it might happen. So there is no regulation. So q2 dot t is equal to minus 3 q1t plus 0 into q2t plus 1 into q3. So q3 dot equation is equal to minus q1t plus 2ut. And when you are representing it, the coefficient of q1 will be minus 1, and there is no q2, there is no q3. Hence the coefficients of q2 and q3 both will be equal to 0, and these two things will be 0. So in q3 dot equation, we are finding q2 and q3, they are not there, but input is there. So that's why the input is there. Now you are finding that q1 dot input is having coefficient of 1 of ut. That's why the here in B matrix top row, this is having 1. In q2 dot, you are finding that ut is having coefficient as 3. Hence in the B matrix, the second row is 3, and in the q3 dot, you are finding the ut is having coefficient of 2. Hence in B matrix, the bottom row is having coefficient as 2. Okay, and YT matrix already I have explained, that is YT is equal to Q1T. How to represent that? This is 1, 0, 0. That means in output there is no mention of Q2 and Q3. But you have to write YT in this format. So don't write YT is equal to Q1T. That will be wrong because in that case we are not writing what is C matrix. So you have to write YT in the form of C and D matrix. D matrix is 0 because there is no direct transmission. but C matrix has to be there. So this is a numerical which is third order, which can be the maximum difficulty level in the exam. And why companion form? Because if transfer function is given, or if a state equation is given, from there we can find out what is the companion form, and companion form helps us to write down this q1 dot q2 dot q3 dot equation in a very easier systematic manner. In the previous RLC numerical, you might have found, so it was not difficult numerical, but you might have found writing state equations and again rearranging them in q1 dot is equal to some coefficient of q1 plus q2 and xt. Again, q2 dot is equal to some coefficient of q1, q2, xt. So that rearrangement and which equation to take, which equation to formulate, you might not be knowing at certain times. That's what I always prefer, that draw the schematic. It takes some time. Okay, so after drawing the schematic, 3 minutes you have to give to draw the schematic, which is actually very easy. Then very easily you can find out what is q3 dot, what is q2 dot, and what is q1 dot equation. From there, very easily you can find out what is q1 dot, q2 dot, q3 dot, and from there, if you write it in matrix form, you can find what is abcd matrix. So this is a standard procedure that I follow. Same thing when the state variable matrix is given, you can find. So this was the numerical one. Then next numerical, we are doing something already we have done in the third module. So let us see, this is a new type of numerical. A state variable representation of the system model is given here. That means x dot t is equal to axt plus but. So see here, here we are not writing it as q dot or q. We are writing as x dot and x. So don't think in your mind that x is always taken as the input. So state variable also can be given as x dot. So state variable representation of the system model is given. Here the state variable x1t is assumed to be the output. So yt is given already. So in this case, x dot t is equal to axt plus but is very clearly given, and yt is equal to x1t. That means what more important thing is given is what is the input. So this is you what is the type of the input. So in this case, it is mentioned that ut is equal to 1. Okay, that means whatever. Okay, so in this case, you are finding that the x dot t is equal to axt plus but. This is given very clearly. And in this case, the state variable is not q1, q2, but in this case, the xt, whatever is written, it will be 2 by 1 matrix of x1, x2. X dot t will be a 2 by 1 matrix of x1 dot t and x2 dot t. A matrix always is square matrix because it's a second order system. How do we know this is second order system? Because A matrix is having dimension 2 cross 2. That means number of state variables would be equal to 2. Whenever number of state variables equal to 2 means it's a second order system. That means there are two energy storing elements in the system. So what you find is A matrix is 0, 1 and minus 2, minus 3, 2 cross 2. You are finding that a B matrix is 0, 1. That means in x1, the ut part is not there, because while you are writing the x1 equation, you are writing that x1 dot t is equal to x1t. That is the top row of the A matrix and B matrix. So in x1 dot t, there is no, sorry, x1 dot t is equal to x2t. I'm sorry, because it is 0, 1. Okay, so x1 dot t is equal to x2t. So there is no x1, there is no ut in the x1. And what is x2 dot t? X2 dot t is minus 2x1t minus 3x2t plus ut. Okay, so this is how the system has to be read. And yt is equal to 1 comma 0, because it is already mentioned in the numerical that output is x1t. So yt is equal to x1t, which means that C matrix is 1 comma 0. There is no D matrix. So in this case, what is new? New is I am giving you ut is equal to 1. That means I have mentioned the input to be unit step for the first time. So I told you that this ut can be unit step, unit ramp, or it can be sinusoidal or any kind of input. Okay, but this for the first time I am telling you what is the input, because what is asked, Now I'm going to go to the numerical and read what is the statement of the numerical. It states that a state variable representation of the system model is given. That means ABCD matrix is given. C matrix is not given, but instead they have told you YT is equal to X1T. So from there you have to find out or mention that C matrix is 1 comma 0. So for the step input, find the time domain equation of the system response YT for the given system. Now this is the numerical. So what is the question for the step input? That's why it is given as ut is equal to 1. That means whenever you are finding what is the response of the system, for that you should know what is the type of the input. So for step input, find the time domain equation of the system response yt. Okay, that means what is asked actually, they have given me ABCD matrix. So from ABC, so what all things you have to do that I'm explaining, you are given with ABCD matrix. From there, you have supposed to find out what is the system transfer function. So what is the system transfer function? It will be ys by xs. Okay, so ys by xs will be a polynomial by polynomial in that form. Then you have to take the xs in the right side, and you have to substitute xs as 1 by s, or us as 1 by s. I'm sorry, not xs. You have to find out ys by us. So because in this numerical, u is the input. So first you have to find out what is ys by us by using c into si minus a inverse into b plus d form. D is not there. So in this case, it will be c into si minus a inverse into b. From there, substitute C matrix, substitute A matrix, find Si minus A inverse, substitute B matrix, find transfer function, Ys by Us, substitute Us to the right side, substitute Us as 1 by S. Then do the partial fraction and then find the partial fractioned output of Ys, take the inverse Laplace and find what is Yt. So whatever things we have learned so far, that is finding transfer function from ABCD matrix, that fundamental we are using. If we know what is the transfer function and if we know what is the input, then we can find out what is the output in Laplace domain, Ys. This we learned in the third module. If we know what is Ys, then take the inverse Laplace transform and you can get what is Yt. So all these fundamentals from all these different chapters or modules you have to put together to solve this numerical. So given us ABCD matrix, from there you have to find out transfer function. In transfer function you have to shift the input to the right side. So find what is Ys. Substitute the Laplace of input us as 1 by s. Find what is Ys equation, do the partial fraction. From there, find what is Yt. So what is asked is in the numerical, if you see the numerical question, to find the time domain equation of system response Yt. That means you have to find Yt given as input and state variable representation. So this kind of numerical is not formed in the book. Okay, so just from my understanding and to make you understand better how we can use a state variable system for calculation as well as for coding, I'm using all this numerical and I have formed all this numerical and solving it. So x dot t is equal to minus 2x1t minus 3x2. So all these things are given. X1 dot t is equal to x2t, yt is equal to x1t. All these things are given. So take x2 dot t is equal to this. So actually finally what they found out is, so they have used a different approach. You can check that. But you can actually find out c into si minus a inverse into b. From there you can find out what is x1s by us. So that is nothing but ys by us. Okay, so just from here, from the numerical, you can find out what is ys by us. So x dot t is given, xt is given, ut is given, yt is not given directly, but hint is given. So c into si minus a inverse into b plus d, you can find out the system transfer function is x1s by us. And then substitute us to the right side. So x1 is by us is equal to 1 by s square plus 3s plus 2. So s square plus 3s plus 2 is actually s plus 1 into s plus 2. And that you have to multiply with 1 by s. So why am I writing x1s here? Because in the numerical it is given here that x1s is equal to yt. So x1t is equal to yt. So this is written here, x1t is equal to yt. That is equal to multiply this thing, already it is multiplied. So x1 is equal to 1 by s into 1 by s plus 1 into 1 by s plus 2. So this s cube plus 3s square plus 2s, if you are factorizing, you are going to get 1 by s into s plus 1 into s plus 2. And then if you are doing partial fraction, it will be half by s minus 1 by s plus 1 plus half by s plus 2. So what is the inverse Laplace transform of x1s? That is x1t, that is same as yt, that is equal to half minus e raised to minus t, it should be, okay, it is not clearly visible, it should be e raised to minus t plus a half of e raised to minus 2t of ut. Ut is nothing but the unit step to make the system causal. So this is a very important numerical, that is state variable is given to you, and from state variable you are finding transfer function. Transfer function, you are substituting the Laplace of the input, and from there you are finding what is the system response. Okay, so this is another type of input. There's another type of numerical that I have formed and I'm showing you. Next, third numerical and fourth numerical, it is already done. So this is nothing but in different cases I'm showing. That is, I'm giving you a state variable representation of the system. So this is question 3. Find system transfer function from the given state variable. That is, state variable representation means ABCD representation. In this case, D is not there. That means only ABC. That means there is no direct transmission from input to the output. So we have to write down the equation as CS by RS, or YS by XS also you can write down. That is equal to transfer function C into Si minus A inverse into B plus D. So first you have found Si minus A. So in yesterday's numerical, I could not show all these things to you clearly. So first write down what is Si. So Si is nothing but S00S. So identity matrix with multiplied with S. So that is Si. So S00S minus A. Okay. A is given here 1011. So A is always a square matrix. So it's a two-dimensional system. This is a second order system. So Si minus A you have found as, I'm sorry, Si minus A you have found as S minus 1, 0, minus 1 and S minus 1. Okay, and what is the delta now? This is S minus 1 whole square minus of minus 1 into 0. That means it will be S minus 1 whole square. So determinant of Si minus A is Si minus 1 whole square. And then 1 upon delta, that is 1 upon Si minus 1 whole square. And then you can exchange this two terms, okay, S minus 1, S minus 1, so they remain same. And the diagonal element here, the second diagonal element, you have to just do positives to negative and negatives to positive. So this minus 1 becomes plus 1 here. So how to find Si minus 1, Si minus A inverse? You cannot waste much time on this in exam. Okay, so very easily you should be able to find out. That is, first find what is delta, that is cross multiplication in matrix, and then just exchange these two terms, that is 1 1 and 2 2, you have to exchange their position without changing sign, and 1 2 and 2 1, you have to exchange their sign. So if there were plus, now they will become minus. If they were minus, now they will become plus. So this minus 1 becomes plus 1. 0 and minus 1, S minus 1, they have changed position. So what is Si minus A inverse? Is 1 upon S minus 1 whole square into this. Now CS by RS, that is C matrix into Si minus A inverse. Okay, so this S minus 1 whole square I have taken inside. That's what I am finding, 1 by S minus 1. This is 0 by S minus 1 whole square. This is 0. 1 upon S minus 1 whole square like this. And S minus 1 by S minus 1 whole square. This is like this. So easy numerical, easy for calculation. I have taken, maybe in exam they will be asking a little difficult numerical, because we are at the starting part of this module. That's why you should not get scared with numerical, because we are learning the tricks here. Okay, so while learning the tricks, easy numerical should be solved. You practice, and when you become pro, at that time you can solve difficult numerical. Now if you just multiply all these things, so first what we have multiplied is this first C matrix with Si minus A inverse. If you are doing that, you will be finding only the top row is remaining. Okay, only the top row, the bottom rows goes, because the second row element, sorry, second column element in C matrix is equal to 0. And 1 by S minus 1 into 0, if you're multiplying with 1 1, you're finding 1 by S minus 1. So there is a minus here, you can understand. So this CS by RS transfer function is 1 by S minus 1. Now for the same system, if I tell you that yes, now the input given to the system is a step or ramp, now tell me what is going to be CT. Okay, so what is CT? CT is nothing but the output response. So now next step, what you have to do is you have to take the RS to the right side. If it is given that input is unit step, then that RS you have to substitute as 1 by S. Now this CS will now become 1 by S into S minus 1. Then you have to do partial fraction. Then you have to do inverse Laplace transform. And then you could tell me what is the CT equation. So CS by RS, once you find, after that it is very easy to find what is CT if the input is mentioned. So that is a very big condition, that for everything in Laplace domain or everything in state variable analysis, the input should be clearly mentioned to you at every scenario, for every time instant. Another numerical, so this is the last numerical we are going to do today. In this numerical also, they are finding out what is the system transfer function given ABCD matrix. So in this case, D matrix is given. You can find out. Always remember the dimension of the matrices. So here instead of X, we are writing Q. So this is Q1 dot T, Q2 dot T. This is Q1 T, Q2 T. Here it is B matrix. So A matrix is minus 3, 1, minus 2, 0. B matrix is 4, 1. C matrix is 1, 0. And D matrix is 5. So what is the equation of yt? Equation of yt is q1t plus 5ut. I'm repeating, equation of yt is q1t plus 5ut, or yt is q1t plus 0 q2t plus 5ut. In that case, you can write it in this compact form. So these two equations together, they are actually giving us the state variable analysis response for the given system. So what is the system, we don't know, but this much we know, that system is a second order system, and yt is equal to q1t plus 5ut. So this much we know. Again, the same thing, you do C into Si minus A inverse into B plus D. So first you have to find what is Si minus A and what is the inverse of that. So all those things I have done together. So first I have written what is C. So C is 1 0. Si minus A. Okay, so Si minus A is S plus 3 minus 1 2 and S inverse of that. So this is Si minus A inverse. This is B 4 1 plus the same square plus b plus has been taken outside, and this is C matrix, and this is Si minus A inverse, only the matrix part, delta is taken outside, and this is B matrix plus D. Okay, so after all these multiplications and multiplying that over 1 upon delta, you are finding that this part, initial part, it becomes 4s plus 1 divided by a square plus 3s plus 2 plus 5. And then if you are adding that, the final CS by R becomes 5s square plus 19s plus 11 divided by a square plus 3s plus 2. So only difference is this is a strictly proper transfer function, and we have not done realization for this, because whenever we have done some realization, we have assumed that the numerator is having less order than the denominator. Okay, so how to do the realization for this thing also we can see afterward. So this was a third lecture with some this is an extra session with some specific numerical designed for you and executed here. So next week we are going to start with a solution of state variable analysis. So in state space, suppose if this is given, what is meant by solution I will tell you now itself. So q1 dot t is equal to minus 3 q1 t q2 t plus 4 ut, and q2 dot t is equal to minus 2 q1 t plus ut. So q1 dot and q2 dot is there, and we are having an equation of q1 dot and q2 dot in terms of q1 q2 and ut, but we don't have the equation of q1 dot t in a simple open time domain response, like q1 dot t is suppose 3 e raised to minus 2t plus 5 e raised to minus 70. So that is kind of an equation we want for every state variable. Okay, and how can we find it? So q1 dot t, q2 dot t is given, x dot t or q dot t is equal to a qt plus but is given, y equation is given. Using all these things, we can find out what is the solution of the differential. So here actually two differential equations we have clubbed together in the top equation. Now we will be solving for that differential equation, and after finding the solution of the differential equation, which is also called as solution of the state variable form which is given, after finding the solution, we will be able to find the equation of q1 and what is the equation of q2 in time domain. So then only our work will be over. That is, from the state variable model given, we can tell you what is the equation of q1t, what is the equation of q2t. That means state variable equation I should be having in my hand. So it should be like open equation. That equation should not be again taking different variables into it. Okay, so it should be like a mathematical equation. And there, if you are substituting t different values, we should be directly be able to find what are the value of q1 variable at different time instant. Okay, so we want that kind of equation where we can substitute value of t anything. Okay, 0 0.1, 0 0.2, 0 0.3, 0.4, or 1, 2, 3, 4, 5, 6, and we can get what is the value of q1 at different time instant or states of q1. So that part we will next week. So this extra session is being concluded now. Thank you. All the notes will be uploaded today itself.